everybody sits in the same spot. So Tony's going to sit right there when he gets here. You might as well leave it there, right? Where's the car set? Is it here or is it? I think it's this one.
I know, right?
So I figure we're just going to mark. So if I look at this review here, note that there's going to be 5 problems, and you got to do all 5 problems, right? You got to do all 5 problems. So you'll see that there's an op-amp. There's 2 first-order circuits. One is a constant source. The other one is a time-dependent source. And then I split up Chapter 9 into 2 problems. One where you got to derive it, and then you'll do a sort of like a minor check to make sure that your B constant is good. And then there's one where I give you the first order equations, and then I say, solve me the complete solution. Now, why do I do that? Because if I was to just give you one problem for problem 4, what you'll find out here is that that becomes a real issue. Because if you mess up, I mean, what do you want me to tell you? That you almost got the right equation? I mean, I could do that, right?
Yes.
But we're just gonna do that. So let me give you a minute to do 1. Okay? So why don't you start on 1? So I'm expecting this problem to be the easiest one. Anybody else want that? So you should be rocking this problem is the way I look at it. This is the one that's going to make you happy. So the common thing here is to calculate the current and the voltage. So just to be clear, I'm not going to talk more than 2 hours. We got to finish these 5 problems in 2 hours. Turns out I have a 4A review afterwards. And that much talking really kicks my ass.
Bless you.
That's a serious infraction. Okay, how about if we look at this guy? Okay. So I'm not going to do node. I'll do that simple circuit technique. So when I look at this guy, I'm really just sort of like following the currents. So if I have the current here, I'm assuming that the current's going to go in that direction. So I'll label that 1. And then the current splits here, and I should get 2 going this way, and 3 going that way. But if I look at this node right here, we already know that there's no current there. So then the current has to go from here all the way to there. Let's call that 4. So one of the things that we immediately see here, if this is ground right here, that's ground, that means that I have a current going from ground to that node. That immediately tells me that whatever that output node V naught is, has to be negative. Okay, so what I'm saying here is that if I look at this node right here, this tells me, if I look at right here, this implies that V naught is negative. So if I get a positive number, then I know that I have to have done something incorrect. So if I look at this, since I seem to like using x as a node variable, I'm going to continue to use x. So I'm going to say that this node right here I'm going to call Vx. And this node over here has to be V naught. Right? That has to be the knot right there. So what I want to do here is I want to then go in and I want to focus on just following the current. Okay? Just following the current. So if I look at the current here, right, that current I3 tells me that so I could do a couple of things. There's several ways to solve this thing. So if I look at the first node, so note that I have I1, has to be I2 plus I3. That's one thing here. And we also know here that if I look at this voltage, if I look at this current right here, so let me focus on I2 and I4. So if I apply KCL essentially at this node, that means that this current must be the same as that current. Okay, so then what I'm doing here is that I'm applying KCL. So if I look at that, that means that the current I2 must be the same as the current I4, which then means Vx minus 0 has to be the same as 0 minus VO, which immediately implies that Vx must be minus V naught. That's good, right? We expected a sign change right there. So what I did here is that I followed the current just going along this branch. So now what am I going to do? I'm going to go around the other branch here. Now all I'm going to do is that I'm just following the current. So now I'm going to focus on I1 equal to I2 plus I3. I think I was jumping around in my head too much. To be honest, I'm kind of rusty on these things. We haven't been talking about them in a while. So if I look at this guy, so I got to follow the current. So I'm going to look at this guy right here. So if I look at I1, I should get 10 minus Vx. Now note, I'm dropping all the 1K, right? We know that the currents are going to be milliamps, so I'm dropping all the 1Ks. And then that current has to equal I2. Well, we know that I2 has to be Vx minus 0. And then I3 has to be Vx minus V naught. But I know that Vx is equal to minus V naught. So now I can solve for Vx. So now solving for Vx, what I'm seeing here is I'm going to get what? That Vx I'm taking to the other side, so I'm going to get 10. Okay, so that's this term right here. So then I get this term right here. And then this guy should be Vx minus Vx should give me 2Vx. So this implies immediately that Vx has to be 10 divided by 4, which should be what? 2.5 volts. Now I know what Vx. But that immediately tells me here that V naught, which is minus Vx, should be minus 2.5 volts. Okay, so we got our first result right now. So now that I know what Vx is, I could then go in and solve for this current here. Oh, this is a slippery current. So let's see here. So that means if I'm going to calculate I naught, note that 3 and 4 are coming in to that node. They combine and they're coming down this branch. But then I have the current coming up because I know that is that's negative 2.5, so the current has to be coming up here. So if I was to do this in color here, what I'm really looking at is that I'm looking at this current right here. Then I'm looking at that current right there. And it's that current plus that current that gives me I naught. So if I was to sort of like label these, right, just to be clear, so if I did 1, 2, 3, 4, then I'll call this 5, and I'll call that 6. So if I look at this, so then I'm going to apply KCL at output node. So if I apply that at the output node, then that means I should have, right, I naught should be I5 plus I6. But what's I5? I5 has to be 3 and 4. So then it has to be I3 plus I4. And then I6, well, it's just got to be I6. So then if I look at using Ohm's law, and seeing I3 has to be Vx minus V naught, but that's just twice the value now. Right, so this has to be Vx minus V naught, and then I4 has to be 0 minus V naught. Oh, yeah, right, V0, sorry. And then I6 has to be just V naught. Now, we got to be careful here because no, I'm already adjusting for the positive value, right? Technically, there is a minus minus here, but they all cancel out. So if I just use the numerical value here, so this guy here should give me what? 2.5. This guy here should give me minus 2.5. And then I'm going to get 2.5. So these guys cancel to 0, so therefore that tells me that I naught must be 2.5 milliamps. Okay. So note that I was sloppy with my minus signs. Right? Listen. Yes.
It should be 2.5 minus negative.
Yeah, it should be 5. Yeah, because the difference between Vx and V naught is 5.
Let's see, let me make sure that, so, oh, I forgot the 2 here. There's a multiplication of 2. Thank you.
Wait, no.
Right? Because that is the sum of 2 of them.
Yeah, that's right.
Yeah. Okay.
Right? So then that gives me 5 minus 2.5. Right? No. Yes.
Yeah, minus 2.5 plus 2.5.
I'm getting confused with the minus sign. Let me step back. Let's be more careful here.
Why don't we just use I3 plus I4 equal I1?
Say that again?
I3 plus I4 is just I1.
It's just I1.
I1 divided.
Wait, let me see. I3 plus I4 equals I1?
Yeah, I1.
I1 on the left.
I5 has to be I1, right?
Okay. Quit being a smart ass, because that's absolutely right. Right? I should have done that right away. I totally agree. Yeah, that was poor choice. Right? Instead of messing around with the signs, I totally agree. So, you know what? I'm going to erase this mess. And I agree that this guy has to be I1. So if I do that, then I don't have to consider all of this is I1. So then if I look at just I1, it's got to be 10 minus 2.5. And then this guy has to be 2.5, so it should give me 5 milliamps. Nope,
That's 10.
it should give me 10 milliamps, excuse me.
V naught is negative 2.5 though, so it should give you 5.
I agree, but what I did here is that voltage is this way. But if I switched it up, then it should be a positive 2.5, right? So I agree that this is, so I naught is 10.5. Okay, thank you for the help. Okay? Let's go to the next question. Okay, so I'll give you some time to look at these. You're welcome.
Page 10, how did we get 10?
You get 5.
Well, I know, but people shouldn't be getting misled during their reviews.
Just doing the transform on the circular. And that 6 ohms is parallel to 12 ohms. The times 12. You know, if I was giving that up, I wouldn't practice it before. So when I it kind of gives us crazy thing. So I'm gonna have to do the questions I just started doing this morning, so they're not like super clean.
What? Is he saying that? It's fucked up.
Just look at it.
Yeah.
Here is going to be the total. Hey, let's look at this circuit. So, like I said before, I did not spend a whole bunch of time sort of like tweaking these circuits just right. This circuit is trivial. And this is a bad circuit that I would give you the example. So we're going to have to modify this circuit. Right? But you'll see why in a minute. But I mean, if you've been calculating the current of the inductor, which you should be, it still applies. But let's just look at this circuit. So if I look at t equal to 0 plus, I have what? I have this. And then I'm going to reduce that to 1. So I'm going to reduce that to 1 resistor or inductor here. So that's what? That's 1. 1 plus 1 is 2. So I get a 2 Henry. I get a 6 ohm. I get a 6 ohm. I get a 6 ohm. And if we were talking about calculating this guy, right? If we were talking about calculating that guy, draw the nodes. Right? If I make this the ground, where's the ground? What's the voltage of our resistor? 12 volts. So if you said, well, 12 volts, I got to say, like, you're right. Right? So, I mean, I guess we could do this and calculate the current, and then say the current, you know, when I go and I solve for this thing, it better give me 12 volts. But let's change the problem just a little bit. Let's say that we want to calculate this V6 right here. Okay? Because it's 12 volts. Right? We don't have to calculate anything. Okay? Remember, I've given some node and mesh questions and on final exams where it's just like this. And then you'll see people put like 2 pages down. And then there's one who just really just kind of looked at the circuit and said, oh, 2 volts. And I said, right on. Right? And that means that you're paying attention. But if you like doing node or mesh, I guess you're going to do mesh or node. So let's do this again. So the first thing that I got to do here is that I'm going to calculate IL of 0 minus. So if I calculate I of 0 minus, I'm assuming steady state. So that means that the switch is open. So in this case here, this implies that the switch is open. So when I look at this circuit here, at steady state, I really have this. And so if I'm following the current, we could see that this guy right here is giving me the I of 0 minus. But if I follow the current, let's just follow the current real quick. Current comes out of the power supply. Right, comes here. It splits going there, and then it comes back up. And then, look what happens here. I see that this short is parallel to the 2 6 ohm resistors right here that are in series. So what does it do? It shorts them out. So these guys are gone, right? Because we say that they're shorted out. So the short kills them all. So that means that the current of the inductor must be the current of the 6 ohm resistor. So therefore, the current of the 6 ohm resistor must be the current of the inductor, which then must be 12 over 6 gives me 2 amps. Okay. So now the switch is thrown. So now we're looking at 0 plus. And so when I put that 0 plus, I now don't have this open anymore. So my circuit then looks something like this. So I'm going to get 6, 6. Then I'm going to get my inductor here. That's 6 here. Like this. So now, what I'm going to do here is my job here is to then calculate the Norton parameters. So what I'm going to do now is I'm going to calculate Norton parameters. And what are my Norton parameters? I got to get I short circuit, I got to get Rn, and I got to get 1 over tau. Okay, so here we go. So what I'm going to do now is I'm going to remove the load, and then I calculate I short circuit across this point. So remove load, calculate I short circuit. So then my circuit looks something like this here. So that's I short circuit right there. So now I can't kill off these resistors now because I have this wire right here. But what I can do, actually, you know what I should have done? I should have left that inductor in here because I'm seeing a source, because I should have redrawn this. I just realized this is a silly circuit because if I redraw this thing, aren't these two in parallel? So I get a 3 ohm resistor in parallel in series with that, so my circuit really looks like this. Right? Then I get this a 3, a 6, and then I have my 2 Henry inductor. So this makes it a hell of a lot easier to calculate I short circuit. So this circuit really this can also look like this here. Right, so this is 3, this is 6, and we could see that I short circuit has to be the current of the 3 ohm resistor, but because it's in parallel with the 12 ohm resistor, we already know that this guy has to be 4 amps. So if I look at this guy, just this piece right here, we could see that I3 has to be the same as I short circuit, which has to be 12 divided by 3, which then gives me 4 amps. Right? I should have redrawn this instead of just jumping into the circuit here. So then, I'm going to keep it in this form here. So what do? I remove my load. I short that guy out, and you can see that I have to have 3 and 2. Is it in series or in parallel? Let's look at it. So now what I'm going to do here is that now I want to calculate Rn. So now I short this guy out. I got 3 here. I got this load. And then I have this guy 6 here. And this guy is going to be somewhere in here. I got to calculate Rn. So for starters here, if I look at these two nodes, my current's coming where? If I look at my current's coming here, then it has to split here. So if it splits, what happens to the 6 ohm resistor? Why is it a short? Because if I look at this node and that node, they got to be the same. So therefore, it's got to kill off this guy, and it should be a normal resistance here equal to 3 ohms. So if I now have 3 ohms, so then that means then 1 over tau has to be what? Rn. Is this an inductor? Yes. Has to look like this. So then Rn is going to give me 3, and then I get 2. Thank you. So then I get 2. So that will be 2 hertz, 3 over 2 hertz. So then I have tau right here. So now I'm going to write up the solution. So if I write up the solution, what does it look like? So if I write up the solution, I'm not going to have that the IL of T should be I short circuit plus IL 0 minus I short circuit e to the minus T over tau. So if I write this up, we saw that I short circuit was equal to 4. Okay, so 4 plus 2 minus 4 e to the minus 1.5 t. So if I look at this guy here, I'm going to get 4 minus 2 e to the minus 1.5 t amps, or I L of t. Now, does this make sense here? Well, we see that the inductor must be increasing in current here. Right? We're clearly seeing that it's going from 2 amps to 4 amps. So if I was to sort of like plot this guy, we're seeing this guy here. So he's coming in at 2 amps, and then it increases in current up to 4 amps. Well, why does it increase in current? Look at the circuit. Right? Why does it increase? Why does placing this short increase the current?
Well, it's the resistance to be half, or cut in half, once we use the short.
Once we use the short, what do you mean it's cut in half?
Or since they're in parallel, the resistance felt is 3 ohms instead of 6, so the current is able to be higher.
That's exactly right. So what I say here is that we were going to modify the circuit to calculate this guy. So when you look at this, if I know the current here, now this circuit, it looks really complicated, but the one thing that you got to remember here is that that current coming in here is being divided. I have the same 2 resistors, and they're going to the same ground node, so it cuts the current in half. So if I look for the voltage of this, I got to divide the current by half, and then I got to multiply by 6. So I'm really doing 6 divided by 2, so it's got to be 3. Right? So if I now go and I solve for this thing here, so to determine V 6 ohm of T, what we're seeing here is that we have the 6 and the inductor coming in like this. So I see this guy, right? So I'm getting 6 here. So I'm seeing this inductor coming in like this, and then clearly I'm going to get half of this thing. So only half of the current of the inductor comes in here. So to calculate the voltage here, the voltage of the 6 ohm at this point then is then going to be 6 times 1/2 IL, which then says that I can multiply this by 3. So if I multiply this by 3, I'm going to get 12 minus 6e to the minus 1.5 t volts. So very similar to this here, it's got an increase in voltage here. So if I go and I plot this guy, what am I seeing? Well, what was the voltage beforehand? Had to be 0, right? Why is it 0? Because we saw here that when this thing was open, that short killed off that voltage right there. So if I go and I plot this, what we're seeing here is that this guy's coming in, V6 at 0 minus was 0 volts. So then the switch is thrown and this guy jumps up to what? 6 volts. So then this thing jumps up all the way up to here and it goes to 6 volts. So from this line, you can see that this guy's going to increase by a value of 6 volts as it goes from 6 all the way up to 12 at t equal to infinity. So when I look at this guy, if I make this my 12 volt line here, we're seeing that this voltage here then jumps up like this. And this is the voltage of the 6 ohm as a function of time. Now, the question is, does this make sense? Right? Does this make physical sense? And the answer is absolutely yes. And that's because it's really nice and clean if you drew the circuit like this. And you can see when this guy dies off, this guy has to go to that 12 volts. They have to. Right? They have to go to that 12 volt. So, but wait a minute. I thought this was 6. Doesn't it divide the voltage by half? Let me say that again. Doesn't it divide the voltage by half? Right? Because look, that 3 is these two 6 ohm resistors. I'm after that voltage.
They're in parallel.
Yes, they're in parallel. Right? That guy's a little bit tricky. So what that circuit really looks like is it looks like this here. So when you redraw this thing, that 3 ohm is really like this with the inductor. And when that guy goes to a short, these two are still in parallel with the 12 volt, and I get 12 volts, just as expected. Okay, let's go to the next one.
The words you said.
Okay, so let's look at this circuit. So note, as I'm doing these problems, I didn't work them out beforehand. So I think the process is right, but if the numbers are a little bit funny, it's probably because we're making the mistake, right? We're making the mistake. We just got to make sure Limbo stays in the room here. So now let's go back to that. So what we want to do here is we want to calculate this voltage. Now when I look at this voltage here, probably the one thing that you want to pay attention to, you got to look at that source. Where's the UT attached to? That's 6 e to the minus t. So we can see that if I talk about the source, at t equal to 0 minus, we see that the source is only equal to 3 volts. But at t equal to 0 plus, that source now becomes 3 plus 6 e to the minus t. I've seen too many people just say, oh, there's no source at t equal to 0 minus. Not true, right? So you want to pay attention to that, to these little details. So if I want to calculate this, as always, I got to calculate this voltage DC. But the problem is that you can see that this is a time-dependent source. So what we have here is that we have a time-dependent source. So that means I got to derive the first order equation. And I'm going to say this because I saw this on the quiz. They'll go in here and they'll go like, oh, I know what these. I just got to go calculate this guy. Right? Because we're talking about a capacitor here. The problem is, this is not valid. It's not valid because I don't have a constant source at 0 plus. Right? Not valid. Now note, some of you are actually deriving, even for constant sources, the differential equation. And that's totally legit. In fact, that's probably the most common that I see in textbooks. Why do I use this? Because I think it's physical. I think that you're really looking at where did the circuit start at, where does it go to, and how does it do that? That's why I prefer this way than not just starting with differential equations right away. But here we have no choice. So let's write down the equation. So what I'm seeing here, since these two are in series, the current through this resistor must be the same as that resistor, so I'm going to treat them as the same. So if I look at this thing here, I can do a KVL all the way around, but what I'm thinking here is that I'm going to just draw in my nodes right now, just to make sure that we're really clear. So if I draw in my nodes, what I'm looking at is that I'm looking at t equals to 0 plus. So that means I got a source. So I'm going to combine these two resistors like this here. So I'm going to get 3 plus 6 e to the minus t. Then I'm going to have a 4 ohm resistor. I'm going to have an 8 ohm resistor. And then I have my cap. So I have 8. Then I got C here, which is 3/16 farad. So if I look at this, if I put my ground right here, you can see right away that this is Vs. This is Vc. So what I'm going to do here is I think I'm going to apply KCL. I think I can do KVL, but in my mind, I'm seeing KCL as the easy one. Because if I know that current, I know this current, and of course I know that current right there. So I'm going to apply KCL to do this. Yes, sir.
What made you want to take that 2 ohm from the bottom and combine it with the top?
Because they're in series. And I know that the current through this resistor must be the same as that. And so if I want to calculate that voltage, then all I need is the current through the 4 ohm resistor to get that voltage and then multiply it by 2.
Okay.
In fact, that's the solution right there. In the end, when we go to solve the circuit problem, we just got to calculate the current here in order to get the voltage there. So then I'm going to apply KCL. So if I apply KCL, you could see that the current of the 4 ohm must be the current of the 8 plus the current of the cap. So if I look at the 4 ohm, Well, look. There's the voltage right across this guy. So that guy has to be Vs minus Vc divided by 4. And this guy, you could see, is just Vc. So then I'm going to write Vc over 8 plus Vc. Plus IC, excuse me. So what I'm going to do now is I'm going to bring this guy over. Look at, I got my differential equation right away. So if I look at this guy, what am I going to do? So I'm going to write this as a quarter V source equals this guy. Now let's add, I'm going to add Vc here. So if I bring this Vc over, I got Vc over 4. And then I have what? A fourth plus an eighth. That should give me 8/3. Yeah, 3. Sorry about that. I don't know what that, I think I'm thinking resistance. So I'm going to get Vc, and then this guy tells me that it's got to be, I think that's a 16, right? That is a 16. So then I get 316 S hat Vc. Damn, I keep forgetting that 16 here. So now what am I going to do? I'm going to clean it up now. If I clean this guy up here, I'm going to multiply everything by 16.
It's 3/8, right? VC.
Tell me how am I getting, isn't it C times the derivative of VC to get the current?
Yeah, but they're talking about where you have 3 VC, it should be 3/8 VC.
1/4 VC and add an actual 1/8 VC. So it should be 3/8.
3/8. Oh, thank you. Absolutely right. So then if I multiply everything out through this thing here, I should get S hat VC. Then I'm going to get what? 16 over 8, which should give me 2. And then on this side here, I should get 16 over 3 divided by 4 should give me 4/3. So if I get 4/3, then I'm going to bring this guy in here. So then I'm going to get 3 plus 6 e to the minus t, which will give me 4 plus 8 e to the minus t. Right? I think that's clean. Dude, you gotta get this right. Right? If you get this wrong, you're solving a different circuit as far as I'm concerned. So this is the one where you're gonna be sweating. You should be sweating, going like, did I get this right? Okay, did I get this right? Your ass better get that right. That's all I know. So then, I'm going to just do a small check. Remember, this does not guarantee that you have the right solution here, right? The right differential equation. So what this tells me here is that at t equal to infinity, I should get Vc at infinity should be this B constant. And if I look at my equation, it tells me what? It tells me that this guy here, that's the one thing that we want to check. So if I plug this guy in here, I'm going to get what? S hat times B, which is 0, plus 2B equals 4, and then this guy should be 0 at t equal to infinity. So immediately that tells me that B should give me a value of 2 volts. The question is, what does the circuit say? Okay? What does the circuit say? I'm going to go back to the circuit now. When I go back to the circuit, what I'm seeing here is that this guy dies off. This guy's an open. So then, as I go along here, that means that the voltage across this guy must be the same as the V8. So that tells me here, V8 at infinity must be the same as VC at infinity. So if I look at this here, then I got 3 going into what? 4 and 8. It's dividing these guys. So then this should be 8 over 4 plus 8 times 3. Oh, I thought I was off there for a minute. So they match up. That gives me a little breathing room. Okay? So these guys match up. So now, let's go calculate the solution. So what we want to do now is that now we want to calculate the general response. Okay, so if I go to calculate the general response, I'm going to look at my differential equation. Right? My differential equation says that I got to have, let's say, B1 and a B2. And then the natural response forces me to have an A constant. So here we go. So that means here that the voltage of the cap should have a natural response and a forced response. So the natural response should be what? A, E, and then it's minus T over tau. I look at my equation and I say, what is 1 over tau? I just pick it off. It's this guy right here. Right? So then I write minus 2T. There's my natural response. Now, I got to get my forced response. The fact that I have a constant and an exponential means it's got to be B1, B2, e to the minus t. So now my job is to get what? B1 and B2. So now we need to determine B1 and B2. So the way I do that is I take my forced response, right? This is my forced response. I take this and I plug it back into the differential equation. And then I force B1 and B2 to match these guys right here. So let's do that. So now I have S hat VC force plus 2BF has to equal 4 plus 8 e to the minus t. So now I'm going to plug in B1 plus B2 e to the minus t. Okay? So if I plug this in, I'm going to take the derivative of this guy. When I take the derivative of this guy, that guy's a constant, so it's 0. I take the derivative of this, the minus sign comes down, so I get 0 minus B2 e to the minus t. Plus 2 times this response, so I'm going to multiply this by 2, so I should get 2B1 plus 2B2 e to the minus t, and this guy has to equal 4 plus 8 e to the minus t. Okay, so these numbers are nice, because if you look at this, 2B1 has to equal 4, so that tells me that 2B1 has to equal 4, tells me that B1 must be 2. So when I look at this guy, you can see that I got minus B2 plus 2B2, so clearly that's just B2. So I got B2, this guy, so then I'm going to get B2 e to the minus t must equal 8 e to the minus t, which tells me that B2 must be 8. Yes?
We've gotten the B1 just from T of infinity. Very quickly. Yeah.
Okay. So we could have done that. Okay. We totally could have done that. That totally would have worked. I'm just a little bit slower than you are. See, that's what happens as you get older. Now, to be honest, I'm expecting that you guys are actually better at circuits than I am almost at this point. I'm a little bit more polished because I got 40 years on you guys, but I expect you guys to be faster than me and better than me. And you know what? I think that's a high compliment. So then, let's go on. So if I look at the general response, right, so now I got GC of t gives me A e to the minus 2t. I plug in these guys, so I get 2 plus 8 e to the minus t, right? So you can see I only have one thing left. What do I got to do? I got to calculate that guy right there. So now my job here is that I got to determine the initial condition and apply it to get A. Right? Note that this is the exact same process as the second order differential equation. Okay, the second order differential equation, of course, is messier. But here we go. So now I'm going to look at t equal to 0 minus. Okay, at t equal to 0 minus, I'm going to redraw my circuit here, and it should be what? I got to be careful here because remember, at t 0 minus, it's 3 volts. So now I'm going to come in here and I have 3 volts, and then I have a 4 ohm, I have an 8 ohm, and then I have VC minus. Yeah. Once again, we know that it's, did we do this already? No, okay. So if I do this here, I can see that the voltage 0 minus implies that it has to be the voltage across the 8 ohm resistor at 0 minus. So it has to be what? 8, 4 plus 8 times 3, which gives me what? I'm going to get, right, that's the same as, well, that's got to be 3/4, so it's got to be what? But 8 over 12 is 2/3. 2/3 then gives me 2. Right?
It's the same as at infinity.
Right? Which is the same as the infinity. That's what I'm saying then. Did we do this already? We sure did, right here. But when we went and did this check, this is the exact same thing that we did. So that means it's going to start, and then it has to jump back to its original value. So then I have VC of 0 minus. So that being said here, now I'm going to apply this condition to this guy. So now applying VC of 0 minus to get A, we then say that VC of 0 minus, which is 2, which is the same as A e to the 0, which is 1, plus 2 plus 8. So if I have that equal to 2, you can see that this 2 and this 2 cancel out, so then A has to be negative 8. So this implies here that A has to be negative 8 volts. So now I have my complete response. So the complete response to that source is VC of t is going to be minus 8 e to the minus 2t plus 2 plus 8 e to the minus t volts. So now I have the complete response. So now I'm going to use this to calculate the voltage here. Now, I kind of hinted that it had to be that solution right there. Right? It had to be that equation. So when we come back, if I know to get this current, I need that current and that current. Right? That's one way that you could do that. But damn, that's got to be messy as shit. Right? You got to get the current of the 8, then you got to get the current of this, which then you got to multiply this by VC times that, and then you got to get IC, and you got to take the derivative, and then you got all this crap. Or you could use KVL. Right? Do I know the source? Yes. Do I know the voltage? Yes. Yeah. Do not do it this way. This is suicide. Right? That's suicide. You will not have time on your exam. And as you can probably imagine, I'm in a very difficult position of writing a fair exam for the amount of time that we have. Right? One mistake on my circuit, that circuit may take you the whole exam. So I got to be really careful. Okay? So what I'm going to do now is that I'm going to solve for the voltage V2 ohm of T. Okay? So what I'm going to do here is that you can see that I know that voltage. Right? I know that voltage. So I can see here that the voltage of the 4 ohm has to be Vs minus Vc. But note, this guy is dividing the voltage across these two resistors right here, right? So that means that V2 has to be half of that voltage. So this implies here that the voltage that we're after is half of V source minus Vc. So then I just start plugging it in. So if I start writing this in here, I'm going to get 1/2. Where's my source? Right here. So I'm going to write 3 plus 6 e to the minus t. And then I get this term that I got to add. So it's got to be minus minus, so I got to be careful here. So the first term is positive, so I'm going to get 8 e to the minus 2t. And then I got two negative terms, which will be minus 2 minus 8 e to the minus t. And so that gives me the voltage here. So what I'm seeing here, that I'm going to get what? 3 minus 2 gives me 1. So this guy has to go to 1/2. And then I'm going to get, and then if I add these two together, right, I should have been careful here. Right, so 1/ of the purple tells me the constant. Double underscore is going to give me these guys right here. And so this gives me 6 minus 8, so I should get minus 2 e to the minus t. And then this guy's, oops, I got to divide by 2 though. Right, then I divide by 2, and then this guy divided by 2 gives me plus 8, oops, plus 4 e to the minus 2t. So then this is the voltage of the 2 ohm for t greater than 0 in units of volts. So now, does that make sense? What did we say? Vc at t infinity, we would expect this guy. So if I look at the circuit here, what do I know? So let's plot this guy. Initially, this is 2 volts, right? This is 2 volts. Maybe I'm making too many steps. Let's see if we can do this without rewriting it. At t infinity, we agree that this guy's gone. This guy's in open, and we already calculated that this was 2 volts. So if I do a KVL around like this here, if this is 3 and that's 2, that has to be 1 volt. Right? So if I look at the circuit here, what we're seeing here is that at t equal to infinity, we're seeing here that the voltage across the 4 ohm has to be 2 volts, which then implies that the voltage, oops, I said 1 volt, that the voltage across the 2 ohm resistor must be half a volt. So when I look at this guy, you can see that at t equal to infinity, that term drops out, that term drops out. That's good. So we know it's got to go to half a volt. The question is, what is it at t equal to 0? So at t equal to 0, note that this is 4, and then that's a half, so that's 4.5, and then I'm going to subtract 1, so that gives me 3.5. So at t equal to 0, what we're seeing that this guy's at 3.5 volts. And what's it going to decay to? It's got to decay to 1/2. So you can see here that let's make this value here the 1/2, so the voltage equal to 1/2 volt. So we see that this guy has to decay down to this value right there. What is V2 at 0 minus? It has to be exactly the same thing, right? At t infinity that's there, but at 0 minus that's not there either. So that means that this guy comes in and it does what? It comes in at half a volt for V2 at 0 minus, and then it jumps up to there. There's a discontinuity And then I get that behavior right there. So this exponential, what did it do? It gave it a pulse. And then as soon as that pulse decays, it goes right back to where it started at. Okay, let's go to the next one.